Hello and welcome to Signal Systems and Signal Processing with Wolfram U. The topic of this lesson is discrete-time Fourier transform theorems. In this lesson, we will go over some of the important properties of Fourier transform, such as linearity and conjugate symmetry. We will also discuss a few theorems, time shift, time convolution, and Parseval's relation. The discrete-time Fourier transform x of e to the power j omega is periodic with period 2 pi. If omega is shifted by 2 pi, the Fourier transform will be equal to the expression shown here. Breaking down the exponential term and simplifying, we get x of e to the power j omega. So the Fourier transform is periodic with a period of 2 pi. Given the two transform pairs, x of n and its Fourier transform and y of n and its discrete time Fourier transform, the discrete time Fourier transform of a superposition of sequences x of n and y of n, that is a times x of n plus b times y of n, will be a times the Fourier transform of x of n plus b times the Fourier transform of y of n. For example, given the two sequences x of n and y of n as defined here, let's use linearity to find the dtft of the difference of the two sequences x of n and y of n. According to the linearity property, the dtft of x of n minus y of n is equal to the difference of the Fourier transform of the two sequences. So evaluating the difference of the two Fourier transform using the Wolfram language, we have the value shown here. Here we have a plot of the difference sequence in time and its Fourier transform in frequency. We can confirm this result by directly evaluating the Fourier transform of the difference sequence, as shown here. The next property is conjugate symmetry. The discrete time Fourier transform of a complex conjugate of any sequence is equal to the complex conjugate of the discrete time Fourier transform of that sequence. Also, if x of n is real valued, its transform is conjugate symmetric, as indicated here. This means that the magnitude spectrum is an even function of frequency and the phase spectrum is an odd function of frequency. Or the real part of the discrete time Fourier transform is even and the imaginary part is odd. To prove the conjugate symmetry using the time reversal property following the definition of the discrete time Fourier transform, we take the complex conjugate of the discrete time Fourier transform, substituting m equal to minus n, and simplifying, we get the discrete time Fourier transform of x of n. Given a sequence x of n and its discrete time Fourier transform, the Fourier transform of a time-shifted version of the sequence x of n minus n0 that is the discrete time Fourier transform of x of n multiplied by an exponential term with the exponent equal to the amount of the time shift. To prove this property using the definition of the discrete time Fourier transform, we have the expression shown here. Using a change of variable, let m be equal to n minus n0, then the summation will be as indicated here. Taking out the constant part, the remaining sum is the Fourier transform of x of m, and this completes the proof. Note that the magnitude of the Fourier transform stays unchanged as a sequence is shifted, and it is only the phase that is affected by the time shift. Given the sequence x of n shown here, let's find the discrete time Fourier transform of the sequence y of n in terms of the discrete time Fourier transform of x of n. Now, the Fourier transform of the sum will be the sum of the Fourier transform of the two terms in the summation because of the linearity property. And the Fourier transform of the shifted x of n is the Fourier transform of x of n multiplied by the exponential term e to the power j 4 omega, as shown here. If x of n, y of n, and h of n are three sequences related by the equation shown here, y of n is the convolution of x of n and h of n. Then the Fourier transform of y of n is the product of the Fourier transform of the two sequences x of n and h of n, as indicated here. Basically, the convolution of two sequences is mapped to the multiplication of their Fourier transforms in the frequency domain. This again will be helpful in the analysis of signals and systems since multiplication is easier to understand compared to convolution. The proof again comes directly using the definition, replacing the convolution of h of n and x of n for the new sequence and applying a change of variable, replacing n minus k with m and changing the order of two sums. We get the expression for the Fourier transform of x of n, and the remaining terms give the Fourier transform of h of n. We have the product of the discrete time Fourier transform of x of n and discrete time Fourier transform of h of n. As an example, let's verify the discrete time Fourier transform convolution theorem given the two sequences x of n and y of n as shown here. First, we can find the convolution of x of n and y of n using the Wolfram language. Once we have that value, we can take the discrete time Fourier transform of the convolution sequence. And now to verify the theorem, we can compare the result by the result of multiplying the Fourier transform of x of n and Fourier transform of y of n. The result verifies the convolution theorem. Given a sequence x of n and its Fourier transform x of e to the power j omega, then the energy of the sequence in the time domain is related to the energy of the sequence in frequency domain using Parseval's relation. The relation states that the total energy of the sequence x of n can be determined by integrating the power spectrum over a 2 pi frequency interval. Let's verify Parseval's relation for the sequence x of n defined as shown here. We can evaluate the energy using the time domain definition of the sequence as shown here. Now, we first find the Fourier transform of the sequence and then evaluating the energy using Parseval's relation gives us the same result. This verifies the Parseval's relation. In this lesson, we went over some important Fourier transform properties and theorems, such as linearity, conjugate symmetry, time shift, time convolution, and Parseval's relation. We went over some examples with applications of the properties and theorems in solving several elementary signal processing problems.